Hi, my name is Masih and I present our joint work with Bastian Kuth, also first author, Max Oberberger and Quirin Meyer. So let's get started. We can model a 3D mesh not only with triangles, but we could also use bicubic Bézier surfaces. And now you may ask yourself why we should use bicubic Bézier surfaces instead. And in fact, they have some advantages as opposed to triangular meshes. They are superior for representing smooth surfaces. They can be naturally extended to other variants such as higher order and rational ones. And it's more intuitive to modify them. You have a bunch of control points. And it's also more convenient to generate multiple levels of details for them. And you need initially fewer vertices. Yeah, now let's take a look at the big guy as a popular example of a bicubic Bézier surface. It consists of a bunch of base patches, and we can take a look at one of these base patches. If we zoom in, we see that we have 16 control points that form our smooth surface and its convex hull, and probably you know this formula, you saw it in your lectures. That's a way to evaluate a point on the surface. It's quite simple, but it's not that straightforward to render such a surface in comparison to a triangular mesh. And the most straightforward way to do that is nowadays using tessellation pipeline. But the problem with that is you get some sort of ugly predefined topology, and you have also some over-triangulated results, as we see later. And the more elegant approach would involve subdivision, as we will see now. Yeah, and we will use a similar technique as Eisenach et al. Did in 2009. They used NVIDIA CUDA back then for the compute pass and OpenGL for the graphics pass. And they had cracks because of the non-uniform subdivision, and they tried or attempted to hide the cracks, but the results were still not watertight, and their approach was also memory and bandwidth intensive. So we will address and solve these issues. Now let's take a closer look how we can render such a surface recursively. Let's start with our base patch. Again, it's a bicubic Bézier surface, and let's get rid of the control points. What we do is we kind of try to approximate our surface with two triangles. Both of them are coplanar, and if it's enough, if this approximation is enough, then we can render it, and if not, we have to take our base patch, subdivide it into smaller subpatches, and then apply the very same algorithm to each subpatch. Now the main question is how we take this decision when we have to subdivide and when we have to render. And we answered this question as part of our contribution. We came up with a two-tier test. First, we have an HDR, and if our surface passes the HDR, if it does not pass the HDR, we proceed with the subdivision. And if it passes the HDR, we will proceed with the inner tier. And the very same thing applies to the inner tier. If we do not pass that, we have to subdivide. And if we pass it this time, we can proceed with rendering and then render the surface with two triangles. Okay. Now, let's take a look at the HDR. If we go back to our surface, what we see here, we have a bunch of curves at boundaries, and we call them boundary curves. And if you zoom in to one of boundary curves, what we could do is we could go ahead and say, let's suppose that we have a line that connects both endpoints of the curve, and we could go ahead and evaluate the curve at 1/3 and 2/3. They are the inner points, inner control points or Bézier points of the cubic Bézier curve, and then compute the orthogonal distance to the line. And if these distances are larger than a threshold, we say, oh, we have to subdivide. And if it's not the case, we can say, okay, now it's time to proceed with the inner tier. And now we're done actually with the HDR, and we can proceed with the inner tier. In the inner tier, we have a quite similar thing, but we extend the very same idea that we saw in the curves now to the surface and evaluate our surface at its inner points, and again calculate the orthogonal distances and see if we are larger than a threshold. If yes, we have again to subdivide, and if not, we can this time proceed with the rendering. That looks actually good, and we get good results, but there is a problem there. The hexagons here shows the parametric coordinates, and here we have a perfectly flat surface that looks actually good, but something can still goes wrong, and that is that our control points, our inner control points, could still skew the parametric coordinates. That will lead to a distortion. I mean, the geometry and silhouettes are both accurate, but we will get some shading artifacts. We want to solve that. Now, in order to solve that, what we do is we say, okay, we could go ahead and we could go back to our curve, for example, and this time we can also evaluate the line at the very same points, 1/3 and 2/3. And this time we do not calculate we do not only calculate the orthogonal distances, but also the parametric distances. They look a little bit different, and we have to apply the very same thing also to the inner tier. And by doing that, what we will get is the following thing. You can see we have more geometry, but they're a little bit smaller at the edges, and we can solve the distortion, but we have a problem. We have too much geometry, so it's kind of over-triangulated. In order to solve that, we do interpolate between two metrics with a lambda value and merge them together into one unified subdivision criterion. And you can see the results on the left. So what we have here is we kind of interpolated exactly at the midpoint of both metrics, and we could still solve the distortion, but we also have much less geometry. So we have kind of a trade-off here. So, and you can also play around with that value if you want. So now let's take a look at one of the other problems that we had and we had to solve. And imagine we have two neighboring patches, and they are both at the very same level, subdivision level. Now the problem is that one of them, based on the subdivision criterion, kind of decides to get subdivided one level more, and now we have a corrector. It's, again, as I said earlier, because of the non-uniform subdivision. And the way that we kind of solve that is we say, okay, let's add a triangle there. It looks actually trivial, but it's not. It was quite a lot of work for us. And we call this triangle a wedge. And you can see also our wedge and other patches in the parametric domain here. And we have a shared edge here, and that's the yellow edge, and we have a wedge pivot. Now the challenge is which thread should draw that wedge. And since we store the crack fixing information, we know which edges basically at which level were fine enough to kind of stop with the subdivision. And the one in the finer level will use that information to kind of fill the crack with a wedge without communicating with any other thread or any other patch. So, and we need that because we need to kind of show the consistency of our computations at the edge tier to get a watertight resolution. And it's kind of similar to the outer tessellation factor of the hardware tessellation if you have worked with that. So now, that we know when to subdivide and how to close the cracks, let's take a look at how we can perform the subdivision itself. We have our bicubic Bézier surfaces here, and what you could do is you could go ahead and compute the subdivided Bézier points and then pass the points computed to the next recursion level or recursion call. That's quite easy and convenient, but the problem is that you will end up having 192 bytes per patch because you have 16 control points per patch, and each of them is a 3D floating point. That's not actually good. We don't like that. We want to do something else. We want to reconstruct a curve, or in this case, reconstruct our surface through subdivision. So, and we use a quad tree, and each patch has a node there, and we need this information. We need the patch ID because we reconstruct our sub-patch from the base patch, so we have to know to which base patch we belong, and we need the depth, obviously, to kind of reconstruct the surface, and also the XY coordinates, or MN coordinates in this case, in our quad tree, and we have also this crack fixing information here. Now, with that, and using bit fills, we will end up having 8 bytes instead of 192 bytes. Okay, so that's kind of good. Yeah, it was also part of a contribution. Now let's take a look at a curve, how we could do the subdivision, and later on we will extend this idea to the surface and solve also the issues that we will see later. We start with our cubic Bézier curve, and we want to reconstruct the subcurve from the base curve. That's an arbitrary base curve, and what we could do is we could subdivide at the last control point, or evaluate at the last control point, take the left curve, and then this time evaluate at the A divided by B, and then only consider the right curve, and that's it. Now, that looks actually good, but if you want to reconstruct another neighboring curve, we will end up having a floating point division, which is not good. You don't want to have that because you get some sort of discrepancy here and you will have some cracks. So that's not actually good. We have to solve that. And that will also not be compatible with your crack fixing method. So that's not actually good. And you probably have worked with the Costello's algorithm you have heard about. The way that it works is quite simple. If you want to evaluate the curve at a specific point, you kind of interpolate between the control points pairwise and successively, and you do that with also the results of the first level, and you do that until you get a last point, and that last point, in this case the orange point that you see here, is the point on the curve. But we also get a subdivision result here. We will have the 4 control points of the left curve and also 4 control points of the right curve. So we can also extend the very same idea to blossoms. It's more abstract version of them, and we can use that for reconstructing our subdivision that looks actually like this. It's a function that takes some parameters and maps it to 3D real vector, and we need following blossoms for that. And that looks actually good. We can extend it to the curve of curves approach, which means we first subdivide in one direction, or reconstruct in one direction U, and then in the other direction to get our sub-patch. But the problem is, if you look a little bit further, maybe we have a neighboring patch which is kind of rotated, and that will also screw our results, so that we don't want to have that because of the discrepancy, obviously. And what we could do here is we could go ahead and say, okay, that's also not good, but we can extend the 1D blossoms to 2D blossoms and use the surface blossoming. And what we do there is we do successive bilinear interpolation, and as maybe you saw it here, once again maybe, I don't know, yeah, you can see that here. And the problem is that we have, again, bilinear interpolation. That's, again, floating point arithmetic. That's not actually good. And what we do is we define a cross-like order to kind of make sure that it doesn't matter in which order we compute, we will always get the very same thing or very same results. And we will have the one diagonal first and the second one, and then we mix and merge both results together. And you can see that also in our code. And the most important thing here is you have to mind the computational order and also the correct parentheses. That's really important. Okay, and with that we will get our computations rotational invariant. So we fix all of these problems. Now let's take a look at our work graphs implementation, because we implemented all of that in work graphs. And also, I mean, beside to execute direct and other implementation, we start with our entry node, which is a broadcasting node. We will get our base patch. We will take a decision. Okay, do we want to render or do we want to subdivide? If we want to render, we will pass it to the bundle codes. It's a coalescer. It's kind of optimization. I will say something to that later. And if not, and if we have to subdivide, we will pass it to a thread node. And that works on a base patch. And a quad node does a quite similar thing. It will take a decision, do we want to render or do we want to subdivide? And if we want to render, we have to pass it to bundle quads. If not, we have to recursively call the very same node. And that's an interesting point about the work graphs. You have trivial recursion in comparison to usual GPU programming that you did. You do not have recursion in your shaders. And in the bundle quads, it's kind of the optimization that we had. You bundle the work items together and then pass them once to our mesh node. It's like a mesh shader. And there we will render the quads as a bunch of triangles. Yeah. So that was our implementation. Now let's take a look at the evaluation. We came up with our custom kitchen scene, which consists of a bunch of common test measures for bicubic Bézier surfaces. We have roughly 36,000 base patches. And we also rendered the scene from different camera perspectives. As you can see here, we have the native view multipod, as you probably know, and also other nice looking models. And we use that to kind of compare the quality of our implementation to a ground truth. And for ground truth, we use hardware tessellation as the state-of-the-art way to render such patches. And there we use the maximum level of or factor of tessellation to kind of be our ground truth. And as you can see here, we generate similar or better results in subdivision in comparison to tessellation. And we also did some performance evaluations. Our contribution requires less geometry than tessellation at the same quality. That's one of the advantages that we have. And if you only account for the geometric accuracy, I mean, if you don't really care about the shading artifacts that I mentioned earlier, you end up having even less triangles. And yeah, we will be quite faster. And we can also outperform the tessellation. Okay. Yeah, now let's take a look at the memory requirements. Tessellation is an opaque feature, so we do not have any information about the internal memory requirements of tessellation, but execute indirect needs 1.5 gigabyte roughly. Our work graphs implementation needs only 27 megabytes. And the good thing about work graphs is that with that 27 megabytes, we can kind of go up to 10 level of subdivision, but in the case of execute direct, in this case, you are bound to 6 because you have only 1.5 gigabyte only. And the reason why we have that amount of memory is that we need 2 buffers for our ping pong and subdivision, and a final buffer for the geometry. And in the case of work graphs, we only need the baking memory, which is determined and also managed by the work graphs runtime. In the case of execute direct, it's managed by developers, and you have to do it for worst case, okay? So now let's take a look at the implementation effort. Tessellation is the easiest, then comes the work graphs, and at the end, execute indirect. The reason why tessellation is easy because it's actually designed for patch rendering. The work graphs is also quite easy because you need only a single dispatch on the host, And in the case of execute indirect, you need multiple dispatches, you have multiple buffers, you have to allocate them, you have to manage them, and you need 4 different compute kernels, and you need atomic counters and also synchronization to get everything done. And but the very same functionality can be used in both forecrafts and execute indirect. And now let's list our contributions. We came up with a sparse representation for our subpatches. We kind of design numerically stable and fast reconstruction algorithm. We have a novel controllable subdivision criterion for v-adaptivity. And we have a communication-free crack closing technique. And we also designed our computations carefully so that we can kind of get watertight triangulations. And we have an intuitive implementation with GPU work graphs, but still we are independent from GPU work graphs. You can take the very same code, put it into a common shader file, and use it in the execute indirect one, the mathematical functions. And in the future, what we want to do is we want to extend our ideas to Catmull-Clark subdivision surfaces, and also check whether we can use work graphs for other recursive split problems like level of details creation and rendering, or creation and traversal of BBHs. And also other applications. Now take a look at one of our videos. On the right-hand side, you can see a QR code to our GitHub repository where you can download and look at the code with all the utilities that we had with the test meshes. Yeah. And on the left, you see the tessellation. On the right, you see our subdivision. You can see that we do not have that ugly topology. And also, in most of the cases, you can see in tessellation that the concentration of geometry at some points are is really high, and you have over-triangulated results. But in our subdivision case, we do not have that. And yeah, it's, by the way, the kitchen scene that I mentioned earlier that we kind of created with a bunch of popular assets for smooth surfaces. So it will be done. Yeah, okay. Yeah, so thank you so much.
Great. Thank you. Do people have questions?
Thank you for the presentation. I want to know that when Bézier surfaces are like skinned, animated, is this subdivision temporarily stable, or is maybe blinking everywhere? Like,
yes, we did not do that, but you could do it, and they are actually temporarily stable. Yeah, you have to kind of recalculate the points once again, but it's not that much a problem because yeah.
Okay, thanks.
Because we do not store them explicitly, so that's not a problem. We do it in runtime.
Yeah, thank you.
It's fine.
Other questions?
Great talk. For the work graphs approach, since you don't have to store any geometry and intermediate buffers, does this ever present issues with, like, if you're doing traditional shadow mapping with geometry and because it's view adaptive, right? The tessellation. Or the subdivision, rather. Did it ever cause issues with, like...
Can you elaborate a little bit more on the question? I did not get it really.
Like if the light's coming from a direction that's quite different from the view direction, which is what you're tessellating based on. Yes. I'm guessing you're not tessellating, or subdividing rather, if you were rendering the geometry to a shadow map or something?
Yeah, that's a good point. We did not do that actually in this case, but you could still do it. What we do when we do the shadow maps, we kind of render from the perspective of the light, right?
Yeah.
You could still do it, and you could still do the very same thing. But right. I'm not sure. But then you need some sort of, maybe you can do it in a separate node. I'm not sure about that.
Right. Yeah.
Maybe we can speak after the talk about it. I can show it to something else. Yeah.
Sure. I was just wondering.
But I'm not sure about this. Maybe you could do it. Yeah. Maybe in a separate node after, but I'm not sure.
Wondering if it's necessary at all when you evaluate the shadow map, like if...
Yes.
Yeah.
All right, I think we should probably move on here, so if there's further questions, you can take them on offline. So let's thank our speaker one more time.
Thank you so much.